Swayam Prabha. Digital India. Educated India.
Now let us understand what are the different strategies. Already you have discussed few things, but let us discuss in little more detail, like how what are the different strategies whereby which 4D bioprinting can be achieved. Like suppose here the 3D bioprinting, suppose this is an extrusion based bioprinter with which, or maybe it can be a inkjet based bioprinter also, with which suppose we print a certain life site, certain type of structure, certain 3D structures, a particular design we have printed where the cells are also encapsulated within this thing, and suppose two different layers we have printed here with two different two different materials, or can also be uh, same materials or different concentration of the same materials, or different cross-linking density of the same materials. So what will happen, these two layers, they may have different properties. Suppose the swelling properties of these two layers are very different. Suppose that these two layers respond differently to different temperatures. These two layers can also respond differently to different pH. So that all these things are the cues or the stimulus for these changes, for changes of the shape or size of these bioprinted structures. Now suppose after printing these structures, then it can be subjected to different external stimulus, right? Now when a particular different external stimulus is given, then this structure can change its shape, size, or volume. So anything can get changed. Then the structure, suppose this structure can get bend, or can be rotated, can get rotated, or different types of changes can happen. So that can be one particular strategy for bioprinting. So typically for this thing, different responsive materials are mostly used. They are called smart materials, or mostly some smart biomaterials can be used for different types. So these biomaterials can respond to different types of stimulus, and then this changes, this programmable change in size, shape can happen. So all these things are related to, all these things can be related to for the bioprinting. Other things, so time here, and mostly all these changes can depend on the time. So here this is the post printing time, and that upon this time the changes can happen. Other than this, also certain cases bioprinted constructs can get matured, and over maturation, or after maturation, there the again there can be a change in the structure. So that can happen, and that can also be qualified for the bioprinting. Now let again a few more details about this thing. Suppose this is a 3D bioprinted cell and construct, and now if we introduce, or if we excite this thing with different external stimuli, like water can be an external stimuli here, because suppose if the material having two different layers and they have varied swelling ratio, that means if suppose the top layer has one particular swelling ratio and the bottom layer can have other uh, separate different swelling ratio, then what will happen, if I subject this material to water, then what will happen, the higher swelling ratios layer will swell more, and the lower swelling ratio layer will swell less. So then always there will be, if there is a differential swelling, what will happen, there will be a bending. Like this, suppose this layer cannot swell less, this layer swell more, what will happen, this layer will expand more, this layer will expand less. So there will be differential expansion, and due to this there will be a bending, because this whole structure is, the two layers are bonded together. So there will be different types of uh, again same thing. So that can happen due to the swelling, and or that can happen upon introducing water to this thing. So into here water can be used as a stimuli in this case, a stimulus in this case. Then the other things, temperature can also be used as a stimuli, external stimuli, because some material, some thermal responsive material, their changes are mostly induced by temperature change. Suppose these two, again these two materials are suppose made up of two different layers, and these two these two layers are of different materials. Suppose one is of thermal responsive, another one is not thermal responsive. So what will happen? Suppose if I then change the temperature of the structure, one particular material that will respond to the stimulus and the other material will not respond to that stimulus in the same way. So what we can get? We can get a or the expansion or contraction of that material, if it depends on the temperature, then also there can be a bending of the structure, because suppose one material that respond to the temperature, the very different temperature, if we incubate the structure in that particular temperature, that suppose but the bottom layer expand more and the top layer expand less, then what will happen? Then also there will be a bending of the structure. So this shape change can be because of this temperature. Again, similarly for pH also there can be these things happen. Suppose these two different layers can respond differently to different pH, then also the pH can be used as a stimulus for this say change. So these are all called shape. So these are all like morphing of the structures. So these are all called morphing structures, or structures morphing of the structures can happen. The other thing is also, as we have discussed, due to the maturation of the construct. Maturation is a process by which cells, they basically, what will happen, the cell, it depends on the cellular function, the cells will grow in the structure, they will proliferate, they will mature, they will differentiate, or they will migrate. All these things can happen, and then the tissue building process started. So this maturation process, as it is a cell driven process, so then also it can be qualified for 4D bioprinting. But the only difference with 3D bioprinted construct and 4D bioprinted construct is the if the changes can be programmed, or if the changes can be anticipated. If there is an anticipated change, then it can qualify for 4D bioprinting. Suppose the tissue maturation, suppose this is a 3D bioprinted construct, if it matures, but if we can program this change by choosing a particular type of biomaterial, by introducing the cells in suppose we introduce a certain number of cells, and we know that if we put this number of cells, this changes, this kind of growth can happen, so that we anticipate this change. If we program that change, that can be qualified for 4D bioprinting. So tissue maturation, based on tissue maturation also, the 4D bioprinting can also happen based on tissue maturation. So all this process, now all these things can come under 4D bioprinting. If any of these strategies has been used for 3D printing and then post printing changes, so then those studies can also be qualified for 4D bioprinting. So there are different shape memory materials. So the different shape memory materials are being used for 4D bioprinting, because these materials are mostly smart materials, as we said, because they have they can the change of the structure can happen due to some stimulus, and then the changes can be reversible. So there is different types of shape memory materials, like shape memory ceramics, alloys, hybrids, gels, polymers. All these different types of materials are possible. So please read the literature. You will find many more examples of these different shape memory materials for the application in for the 4D bioprinting applications. Now the next thing, let us discuss about the what are the different factors that are actually those are responsible for this 4D bioprinting or post printing changes. Like what are the different ways basically mainly we can control the 4D bioprinting process? As we have said, the different stimulus is the can be applied for the bioprinting. Like if we suppose we print a structures at one particular like structures, and then we provide, then what we do, then we provide some stimulus. After the stimulus is given, then this changes can, if the changes happens, so that there we can the prototype printing depending on the stimulus, what type of stimulus is given, and whether that or the way that 4D bioprinted structures is, or 3D bioprinted structure is responsive to that stimulus or not. So that time this 4D bioprinting, so 4D bioprinting depends on this stimulus here. Again, some kind of mathematical modeling can be employed and has been employed for to understand this 4D bioprinting process. Like this changes, whatever happened, this 4D bioprinting changes. This can be modeled and we can accurately predict or design how much changes, what type of changes, and how much changes can happen in the 4D bioprinting process. So mathematical modeling can also be very much helpful to understand the 4D bioprinting process. And many a times 4D bioprinting process can depend on the mathematical models. So mathematical modeling is another factor or anything, another factor that is also can be studied for 4D bioprinting. Again, for 4D bioprinting, we have been using different types of responsive materials or smart materials. So these materials either can be of thermal responsive, there can be of temperature responsive, there can also be magnetic responsive. That means if we introduce some magnetic, suppose the magnetic materials within the printed structures, and then if we bring a magnet close to the structure, then that magnetic field, that magnetic field in that induced magnetic field on the structure can bring changes within the structure because of the presence of these magnetic particles within the structure. So that is also another way to control the changes of the material, and then in that case also we can program those changes by using this responsive material. So different types of responsive materials we have mostly people use for to do the 4D bioprinting application. Now, fabrication technique is a very important factor for 4D bioprinting because all these different types of whatever the structures we are making, those structures have to be printed by either some 3D bioprinting or 3D printing techniques. So then if we use some 3D printing techniques to fabricate the structures, then only this 4D bioprinting can be employed. So the changes later on, the changes can happen or can be applied if we use certain fabrication techniques. So unless we use some certain fabrication technique, the changes can happen. So that's why fabrication technique is another important factor for 4D bioprinting. The next is this mechanism of interaction. Now we need to understand. So this can be one important factor. We need to understand what types of interaction can happen, suppose with the stimulus, or suppose in case of self assembly or self accommodating process, what type of mechanism is possible. So this also can depend on the, so the 4D bioprinting can be depending on this the different types of interaction. So that also needs to be understand quite well. So these all are the 5 factors on which the 4D printing mainly depends. Now let us discuss a few examples of this 4D bioprinting process, like when actually how we can use different types of materials for 4D bioprinting. So here mostly we rely on either we can use certain type of biomaterials, those are responsive biomaterials, like or smart biomaterials. That means they are responsive towards certain stimulus like water, as we have earlier discussed, water, pH or temperature or magnetic field. So different types of things can be there. Now also another thing we also do, we can use materials where the designing of the structure in such a way that the material, due to the design, the material responds differently towards a certain stimulus. Like a material, 4D printed, suppose a bilayer structure can be printed with for this 3D printing technique. Now this bilayer structure, if the bilayer structure has two different materials having varied swelling ratio in two different layers. So bilayer. So one layer is made up of one type of material having one type of swelling ratio, another layer having another type of material that has another swelling ratio. And if there is a difference in this swelling ratio, then what will happen? These two layers can respond differently towards this towards water. Like suppose you print the structure, then you dip the structure in water, the response of the structures towards this, or the swelling of the structure of the layers, would be very different from each other. Then what will happen? The main layer that is with higher swelling ratio, that will expand more than the layer with lower swelling ratio. Then what will happen? Due to the difference in expansion of this material, there will be always a bending of the material. If there is a similar swelling ratio about the material, then there will be expansion, only the size will increase of the structure. But if there is a difference in swelling ratio, then the structure will the bend. So this bending, due to this bending, there is a shape change, and that shape change can be modeled, or that shape change can be designed and programmed. So that then it can be a 4D bioprinting project. So similarly, so then let us take one example. In one study, a bioprinted PEG bilayer scaffold was developed. Now this is what happens, this PEG bilayer scaffold was developed, but though it is from the same material, but it has in one structure the concentration is higher. Suppose the concentration is higher, and the another layer is the high concentrated, and then the next layer it is the next low concentrated PEG. So in another, we can also have the one layer with high molecular weight PEG, another with low molecular weight PEG. So just the only clue is we have to use this PEG, suppose two PEG materials of different swelling ratio. That can be because of the maybe the higher concentration, change in concentration, or due to the or varied concentration, or can be varied molecular weight, or can be varied cross-link density. Suppose the PEG, in this case, suppose you use PEGDA, PIGDA, that is a photo cross-linkable material. Now, if we now cross-link that material by inducing some light, then the material will be photo cross-linked. Now, if we control the cross-link density, that means the cross-linking intensity of within the structure. In that way also, if we can generate two different to widely differ cross-link structures, then also there will be different swelling ratio, and that also there will be bending if we introduce that to water. So that's why this kind of PG biprinted PG bilayer structures were developed, and then it is being used for as a for programmable shape change or size change. Now this deformation is based on level of water absorption in different compartments of the scaffolds, as I have already discussed. Suppose it is bilayers, two layers, they have different water absorption capacity or swelling ratio, and by this way there is be swelling. Now with this kind of structures, with a proper designing of structure, this kind of 3D responsive scaffolds can be fully customizable to fabricate various anatomically relevant microscale geometries. If we control this, if we can design properly this kind of device, by this way we can control the change of this property, or we can program the change of these devices, and by this way we can actually make different customized structures to suit different anatomical locations. So this has huge potential for different types of 4D bioprinted structures. This technology has a huge potential to fabricate different types of 4D bioprinted structures, and that can respond differently toward different stimulus. Now another study, like an oral delivery device was developed based on the self-folding hydrogel, that is self-folding hydrogels. In this case also, two different layers were printed. In one layer the layer is made up of PMAA, and the other layer is made up of PHMA and PMA. Now PMAA, here this is a swelling layer, it can swell, but PHEMA, that's a non-swelling layer, so it doesn't swell, but if this PMHMA, it will swell. So there is a difference in swelling in these two layers. So due to that, what will happen? The layer that is swelling, that will expand more, and the layer that is not swelling, that will just stay there. So what will happen? Because of this difference in extension, or this thing, so because of the swelling, so the PMMA, it will swell more, it will extend more. PHMA, it will not swell, it will stay there. So what will happen? PHMA, slowly the PHMA layer that will start bending towards this PHMA layer because it is expanding the next, and the PHMA layer is not expanding. So that's why this will get folded. So one group, this Hay et al., this group, they have come up with a oral delivery based devices because their interest is to develop a delivery drug delivery system that can go and develop to the intestine. Because this kind of folding device, what will happen if this changes again? Now here this swelling is also depending on the pH. At low pH there is no so less swelling, but at high pH like pH 8 there is a swelling. Typically in our intestine the pH is, and high it is almost around 8. So in that way, when the pH is 8, this device, with this device it can easily pass through the stomach pH, because it's at low pH it will not swell more, but when it reaches intestine it will swell. With the PMA will swell, it will not see, because in this case there is no swelling, nothing will happen to this. But because of the swelling, this PMA structure, it will get bent and it will bound to the villi-like structures in our intestine. So it can get folded and it can hold the villi-like structure, so that it will get stuck to the villi, so stuck to the intestine, and it stays there. It stays longer in the thing, and it can start and it can release the drug in the intestine for longer duration. So this kind of device, it can, a smart biometers like this kind of can be used, and can be used for a or drug delivery applications. Similarly, Wheeler et al., they have come up with a tissue-like printed material by for using this 4D bioprinting concept for drug delivery applications. What they have done here, in this case, they have used a concept called uh, emulsion, where like the water droplets are printed within a bigger oil droplets. So they have a bigger oil droplets where the surfactants are surface dispersed. Then they have introduced the nozzle within the oil droplets, a micro nozzle, and printed water droplets within this big oil drop. What will happen as soon as the oil droplets come out of the nozzle, and it is in the environment of oil, the the surfactant particles that will coat the water droplet, right, and then they will get deposited within this oil drop. Similarly, when the next water droplet comes, that will also get coated with the surfactant, and that will also go and sit with this with the that another oil droplet. So all these oil water droplets, printed water droplets within this big oil drop, will be discrete, but they will get connected to each other. Now, depending upon what type of surfactant materials you are using, there can be a pore formation, a pore like to formation within. When the two water droplets they connect to each other, there can be a bilayer pore can be developed. Now when this all this water droplet they are connected to each other, and there is a pore. Now if we change the salt concentration within these oil droplets, what will come, because these two water droplet when they connect to each other, if there is a pore formation, then the material inside material can be changed or can be diffused from one side to another side. Now if there is a different salt concentration between these two droplets, what will happen? Due to the osmosis, the water present within these two droplets, so the water from the low low salt concentration to that water will go to the high salt concentrated droplets because of the osmosis, right? So that's why what will happen, there will be a change in shape of the two droplets. The low salt concentrated droplet will contract, and the high salt concentrated droplet will get enlarged. And due to this difference in size, now what will happen? Suppose the bottom layer is printed with high salt concentrated droplet, and the top layer is printed with low salt concentrated droplets. Due to this, what will happen? Because the bottom layer, these droplets are getting bigger, and the small top layer, the droplets are getting smaller. There will be a bending of this droplet structure. So that's why they have called it a tissue-like printed material. Please go through this to literature. This published in Science and Nature Nanotechnology, and also for the other papers you can go through these literatures. Due to the copyright issue, I have not used any of the images, but these studies are very interesting studies. Please go through these literatures for further understanding and further reading.